was building safe and scalable physical AI solutions. Next slide, please. So we've seen some really great success over the past few years in the digital world with AI, and especially generative AI models. And the next big realm is to deploy these type of technologies into the physical realm. And in particular, one area that we find to be very promising and exciting is robotics, and in particular, self-driving trucking. As you can see here, there are many major challenges in the trucking industry that we think that self-driving trucks can help address. There's a large shortage of truck drivers, so potentially increasing the fleet and making the jobs a bit easier by handling more of the miles through autonomy is a big benefit. There's also ways to help potentially reduce accidents and collisions by having systems that can see from a 360 viewpoint and have many sensors and redundancies in place to be safer systems, and potentially also being more efficient with the miles we drive with self-driving trucking. So large and huge potential available for self-driving trucks. And in particular, being able to incorporate AI and machine learning into our robotic systems can really help enable deployable physical AI systems. Next slide, please. So what are the key ingredients for making this type of technology possible? The main challenges in the real world driving is that it's a huge long tail of situations that can happen. And we want to make sure that these AI systems can handle all these different possibilities. You can see here on some of the images on the right, for instance, animals crossing the road, very metallic and specular vehicles. These systems that are all very data-driven, because that's primarily how AI technologies are trained, need to be able to handle these situations well. Next slide, please. And in addition to being generalizable, physical AI systems need to be efficient. This is not just like being in a digital world where you might have a large amount of time available to do processing. If you think about highway speeds, we're moving at more than 60 or 70 miles per hour. There are many things that are happening very quickly. You have to react instantaneously. Our onboard system needs to be efficient and can run at a high frame rate in order to process the moving world. And then lastly, these type of technologies, we need to be very confident when we deploy them that they need to be safe. And this is not just about deploying the technology and seeing what happens. It's more about we need to prove to the public, to regulators, to third parties that the technology that we put in our self-driving trucks can safely maneuver from one location to the next and handle all these situations that we talked about. All right. So at waabi, our approach to autonomy systems is this next-gen AV 2.0, given sensor data, LiDAR, camera, radar, microphones, etc., where we are equipped on our truck that can see the surrounding world. We have a single AI model that takes in that input sensor data, understands the scene. This is considered like the perception and prediction task, and tries to plan a safe maneuver and reason about the system.
The recording has
Rather
stopped.
than having individual handcrafted heuristic models for different parts of the system, we try to have one large system that is able to be interpretable, but can still leverage large-scale training and data to be able to safely maneuver around the scene. And one aspect of autonomy is the algorithm, but the other aspect, which we were just talking about with all those long tail cases, is data. There are so many things that can happen in the real world, especially when you only drive in the physical world. You only see certain things maybe only once in your lifetime. We need to be able to be efficient in how we learn across all these different experiences. And in order to make that data really as efficient as possible in our utilization, we need to leverage simulation. You can see here all these scenarios that we have in this grid are simulation scenarios that are powered through waabi World. And through simulation alone, are we able to leverage all the miles that we encounter and see the rare situations more frequently and train the system to handle these safely. And not all simulation is considered equal. Typical simulation that's sometimes done standardly in the industry is called log replay. You just watch, it's like watching a movie. You just play back the sensor frames and see what happens with your autonomy system. But the truck that drives in the real world is an agent and interacts with all the other agents in the system. So it really needs to be something what we call closed loop simulation. It's kind of like playing a video game. At every time step you make an action, the other actors in the scene are also instantaneously reacting to you in real time, and then you need to make another action and the world updates. And so in this particular case, we have here like a simulation specification that defines what's going to happen in a particular scenario. And then here we have our waabi world diagram, where at every time step, we have a state of the world where all the other actors are in the scene, what map we're on, um, what is the plan maneuvers of what all these actors might be doing. And then every time step, we simulate the sensor data according to the sensor configuration of the truck. We try to plan a maneuver, and then we act on that. Our action is a motion plan, right, or a control signal, but that doesn't always result in the desired output, the plan that we had in mind. We have to take into account the vehicle dynamics of the real world, of the friction, the wind, etc., of what actually happens to the truck as it moves over time. And of course, there's also the notion of latency, which is how do we account for how the compute itself doesn't always instantaneously react. There's a bit of a delay in compute or processing time given the scene. And by that time, the scene might have changed a bit. So this is the waabi world simulation. There's the sensor simulation component, the behavior simulation component of what happens to all the other actors in the scene, latency, and vehicle dynamics. Next slide, please. Yep. And then there are many ways we can specify the type of scenarios that we want to run in simulation. We talked about the real world, where there might be many different situations we see there that we want to recreate in simulation, but that's not enough. We might want to be able to also have users to specify certain scenarios we want to ensure the system is safe for. We might also want to kind of find those needles in the haystack of adversarially optimizing for safety critical situations, just to understand what is that upper bound of performance for the self-driving vehicle. So yeah, these are all different ways you can specify the scenario, and that provides like a rich, controllable set of scenarios that you can then help the autonomy system learn and test against. All right, and now I'll pass it on to Jinkong. I talked about simulation specification, but there's one other key important ingredient to what makes simulation happen at waabi world.
Basically, the simulation specification tells what kind of scenario we want to run in the simulation. And here is another big ingredients is how we can leverage the real world data to building our digital twins. So it's basically like when we drive on the road and we see a lot of sensor observations collected by our sensors. We have the cameras, we have the LiDARs, and the goal is we want to reconstruct everything in the 3D world, not just static environments like the road we drive. We also want to model all the participants, like the vehicles, the pedestrians, and all the other perspectives. And given this representation, we can then, also the specification, we can then render to generate the simulated data, which we will use for training and testing our autonomy. And notice that we not just want to model the representation itself, but also we want to know how the world evolves over time. This is what we call 4D reconstruction. And because we want to cover all the situations that happen in the real world, so we want to reconstruction that be run in many scenarios. So it has to be very scalable. So there are key four features we need for the scalable 4D reconstruction. Yeah, I guess people are familiar with the high photorealism and the controllability. Yeah, we want this to be super accurate, and you cannot tell which is real and same. We want to generate the variations. But I guess we will dive more into the other two aspects that we will elaborate after, which basically no manual annotation and to be efficient. What do I mean by no manual annotation? So basically, existing classical 4D scene representation reconstruction approaches, they are trying to use the labels to distinguish, differentiate the static and dynamics. For instance, you can see here, we have the background, we have the actors. We need to basically tell the model which actor is, what actor it is, and how it moves over the time. And then, given this information, we will render and for the reconstruction. And moreover, existing works they rely on the costly per scene optimization, which is basically we need to optimize thousands of iterations or even longer for one single scene. This is not super scalable. And so because of this, we need a different pipeline, which we'll call unsupervised 4D reconstruction. So this type of pipeline, we want to learn the geometry, appearance, and flow in a fully unsupervised manner. So basically, instead of optimizing one by one, it's not scalable. We want 4D representations with a single network. Just a single forward pass will get in the 4D digital twins. And then we can use for our downstream task. And before we dive into the details, let's take one step back and think about, what's the core idea behind the generative AI models? So taking the large language model as an example, so basically we are just given what we have currently, we are just predicting the next token. And just by this simple self-supervision principle, our models can learn to comprehend very complex human language. Can we apply the same principle into the physical world? So like shown on the right side, once given the sensor observation, and just purely from the predicting the sensor observation, we want to model to automatically learn the structure of the physical world, basically understanding how each participant move in the 3D world, and have a comprehensive understanding about the 4D physical world. Cool. The answer is yes. So this is which comes to our pipeline, which is called Flux 4D, and it's very scalable and very simple. So as you can see here, we just need 3 steps. So first of all, we given our sensor observations, we try to initialize our 3D Gaussian. Here we choose it, and basically we just aggregate the light across different frames, and then we get in this initial Gaussian select. Second, we will pass this initial representation to our network, and then we'll revise the 3D Gaussians, basically tell what's the accurate appearance the geometry is, and more importantly, we need to predict how those particles in the 3D world move. And given this information, imagine that our world is full of particles, and it can be static or dynamic, and it can move, and we can easily warp from the source frame to the target frame, and then render compare with our sensor observations. So basically, this self-supervision is sufficient to provide enough information to supervise our network. And the Flux 4D can automatically learn the dynamics in a fully unsupervised manner. And we found that this approach is super scalable, and it can naturally handle a lot of data because we have a lot of unlabeled data, and the labeling is super expensive and time consuming. And here, as you can see, we try diverse driving scenarios. But here, we can reconstruct so we show the simulated RGB and also our learned flow on the right. And the bottom row is the ground truth. As you can see, our reconstruction is pretty high quality. Yeah, I guess maybe because of the screen, it's not super visible, but as you can see, it's pretty close the flow and also the ground truth flow. And more importantly, we can handle all the pixels because we supervise directly from the image space and all the light space. So we can handle all the perspective objects. For example, also the non-rigid actors like the pedestrians and also the cyclists. And here is another example. We can also handle the high-speed driving scenarios, even not just in front of STVs, also some oncoming actors. We can pretty accurately predict their flow and appearance. And because of our method is super efficient, we can directly run it at scale. Here we show that we can run it on diverse different data set and different scenarios under different lightnings and different density, traffic density. And moreover, apart from the reconstructions, our approach also enables realistic and controllable camera simulation. This is very important for the downstream use case. So because we already know how the particles moves in the 3D space, and then we can simply cluster the points in the 3D space by the velocity, and then we'll get the instant concept. As you can see on the third column, you will see those object concepts, and then you can actually move those objects to create a clean canvas. And then we can also, of course, we can do some novel view synthesis and moving the cameras around and generate those new scenarios. And also we can do in the object manipulations. As you can see on the bottom row, yeah, it's a little bit laggy here, but you can see we can move the actor behaviors, moving it around. Also, we can insert new actors that we construct from another log. Yeah, here is another example. Again, we can get the clusterings, we can generate novel synthesis, and we can get the actor behavior manipulations and actor insertions, removals. A lot of simulation application. And now let's take a look at some cognitive comparisons. As we can see, Flex4D, both we compare two type of approaches, both supervised reconstruction method that rely on the 3D labels, or unsupervised approaches that directly try to learn the information from the sensor data, like ours. But compared with the existing unsupervised method, our approach is learned across many data, and it achieves much more high fidelity. And also, compared with the supervised approaches, surprisingly, we achieve the similar competitive performance while significantly faster. For instance, compared to our last generation generalizable reconstruction approach, GCR, which relies on the labels, our approach achieves better performance by 10 times faster in the reconstruction. And compared to those per-scene optimization approaches like the NeuRAD or 3GS or Unisim, we can achieve 500 times the faster reconstruction speed or 1,000 times faster. And we also compare with those very popular large reconstruction models and some follow-up work that applies to the driving scenes. We found that our approach achieves significantly boost. As you can see, it's a big improvement on the algorithm on the Waymo open dataset. And here are some comparisons. We can achieve better decompositions just by training across many data. However, existing works, they rely on some pre-trained vision prior models or some complex regulations like the cycle consistency or something to decompose those things. So this is the scalability of our approach. And also we can get into the flow estimation more accurately. One interesting thing we can do with this approach is doing the future prediction, because we also use the future frame to train our models. So our model actually learns to comprehend the world, how it evolves. Yeah, compared to the existing method, both the supervised and unsupervised, surprisingly, we find it's even outperformed the approaches with the labels. Yeah, this is because, first of all, we train across many data. So our representation is more robust. So you can, on those extrapolation we use, you can get better performance, even just without any fixers or other advanced techniques. And moreover, our approach, because of we don't rely on the labels, and human labels sometimes it can be inaccurate. So when you try to the filter frames, it might have some flickerings and it's misaligned with the original ground truth. So it will have some artifacts. But because our representation is more continuous, it will be naturally handle those situations. Thus, here we achieve better performance on the future prediction, even if we don't use any labels. And here is one example showing that existing work, they primarily overfitting, they just memorize, cannot doing the nice future predictions on the future frames, but ours can handle it pretty well. Here, last slide, we use the 10 frame path and to predict the next frame future. And we also show that we can try on other data that is very generalizable. It also works on the Waymo and Argoverse and on different scenarios. And interestingly, we want to highlight the scalability of Flux4D. We find that Flux4D is a relatively robust approaches that we find that with more data, actually our performance increase. So here on the left side, we show the performance of flow estimation. On the right side, we show the performance about the reconstruction algorithm. As you can see, with more training data, our performance continually improve, and it seems not saturate yet. So basically, this is exciting because it's on wheels that the potential of our models can be applied with larger scale data and can achieve higher fidelity reconstruction and higher fidelity flow estimation. And also, it can be served as the foundational priors that can be used for pre-training and can be used for other downstream tasks so far. Cool. I guess that's everything for the scalable world reconstructions. And then I will pass to Siva to talk about the safety.
Cool. Thanks, Jinkang. So yeah, this is some really exciting technology Jinkang just presented that's just hot off the press of scalable digital twin creation. And it's a core part of what's going to power like waabi World to enable like scalable simulation. And that feeds into the next part of this talk, which is safety 2.0. We talked a bit earlier just now about AV 2.0, which is this end-to-end autonomy system that's trained on large amounts of data. But the other part is that we need to show that the system is provably safe. And that's our answer, safety 2.0. And the question is, how do we do that? How do we prove that the autonomy system is safer than humans? And if Jinkang can go to the next slide, we will see some of the rare situations one might encounter in the real world that you don't ever want to see more than once, typically. So here's an example that we've captured on our truck, where there is an actor in our lane, large truck. It initially is blocking our field of view. And as you can see, it immediately lane changes, and we see another actor in front of us that's stopped, potentially because of some type of accident or some type of not working engine. And then we have to potentially move onto the shoulder to avoid that actor. So here's an example of a long tail situation we might encounter, and we need to make sure that we can be safe for that situation. And that's just one example, but you can see here in highway and general and public roads and for trucking, there's many rare situations that can happen that can be safety critical. Property damage, small body injury, life-threatening fatalities. These are all very rare situations, and you may encounter them once or not at all. It's very challenging to just assume you can just drive in the real world and see that the system is safe through that manner alone. We need to be able to show that an autonomous system can encounter these situations and would be safe. But as I mentioned before, not all simulation is created equal. If we go to the next slide, we'll see that there are different levels of simulation fidelity that are available out there in the industry, and only a certain level of simulation can be used to help answer the part of whether or not we can have a provably safe system. So there are standard simulation systems that are just meant to test through like unit testing, integration testing, just catch and make sure that the system is working functionally and doesn't crash. Then there are more sophisticated simulation systems that can be used to understand failures of the system, maybe also help provide generating training data for improving the autonomy system by increasing the number of experiences available. But the next level of simulation fidelity is, for a given situation in the real world that you might encounter, what is the exact performance of how your system might behave? What's the exact performance envelope, the threshold? What would be the actual outcome of what happens? And if we can do that, then we can show for many situations how we would perform, and then we can demonstrate a safety case, or it can be one aspect of the safety case of showing simulation for how our system can do well. If we go to the next slide, please. The fidelity of the simulation is critical for being able to do that provable safety. And the key question that is often an aspect discussed a lot in these type of workshops is, for a data-driven simulation, how do we actually measure the realism of our simulation system for evaluating autonomy development? And typically when we think about realism, we might think of, especially for like in sensor simulation or null view synthesis, how well do we reconstruct the original observations, such as through image quality metrics like PSSNR, SSIM, LPIPs, or for lighter point clouds, the chamfer distance or L2 errors. But really the main thing that we care about when it comes to simulation fidelity is that question I asked earlier about, when we have a particular situation in the real world and we see it in simulation, are we able to recreate the same outcome when we have our autonomy system tested in closed loop? So typically when we think about simulation, there's only synthetic scenarios where we kind of handcraft what might happen. That doesn't allow you to compute exactly for the same situation what would occur. So in order to actually develop this new realism measure, we need to come up with like a new notion of evaluation. Typically, when we do simulation, you might have many real-world logs, you might have many synthetic scenarios that you run autonomy with, and then you can compute domain gap metrics. And typically standard in like academia, if you go to the next slide, are distributional metrics. For many different scenarios in simulation and many scenarios in the real world, we might encounter and compute hard breaks. How often do they occur in the situation? We can compute a distribution of that in the real world scenarios, a distribution of that in the simulation, and then compute some type of distribution metric comparing the difference between the two. But this doesn't tell us for the exact same situation what would happen. And that's where paired realism comes in. For the exact same scenario, we can run our autonomy system in closed loop and see what happened in sim versus what would happen in real world. For example, an actor merging into our lane. How often and how exactly do we slow down at what point in time? And when do we resume speed? So that's called paired realism. And And the way we can compute that, show an example here. Here again is the example. So the autonomy system will drive in the real world. It might do a different maneuver in simulation. In this case, we are driving in the same lane. We change and make a lane change in sim. We can compute at every point in time the distance between sim versus real, the location of the self-driving vehicle, and then we can compute this like cumulative relative trajectory error between sim and real for the autonomy system. That kind of indicates to us one system level performance metric of realism for simulation. But as I mentioned before, simulation is typically done like on kind of synthetic scenarios. But in this case, how do we do paired situations? And that goes back to the part that Jin-Khan talked about earlier, which is digital twin creation. If we can build from every snippet that we encounter in the real world a controllable digital twin of the same exact actors, their behaviors, their locations, and appearance, we have the exact same situation that occurred in the real world in simulation. And then we can run in closed loop what would actually happen. So through digital twins, we have this paired setting, and we can then run waabi world like before. We initialize the scene with that digital twin representation, but then everything else is controlled by the system. So we have behavior models that control the actors. We render through neural rendering techniques, the LiDAR and camera data, etc., of the sensor configuration. And then we update the location of the self-driving vehicle at each time step based on the vehicle dynamics of the world. So that causes the potential drift in the simulator because you're executing closed loop. The maneuver and the system might interact slightly differently in sim versus what happened in the real world. And now if we have these paired scenarios, if we have the exact same autonomy system release version in the real world that drove for a particular situation, we can take that same release autonomy, the same digital twin scenario, and then run that in closed loop in sim and see if we're able to reproduce the same behaviors. So we have done that on a set of scenarios, and we were able to demonstrate that waabi world has a realism of around 99.7%. We can show here one example scenario. So in the real world, this was the waabi driver driving and making a lane change to take the off ramp. And then in sim, we have the same situation happening, and we can show that we can model all the actors, simulate the sensor data, and create the same type of maneuver of the exiting off the off ramp at the same point in time. And also handling, for example, these traffic merges is another scenario, for instance. Cool. And we just talked about now one metric of simulation realism, which is, do I behave the same way in simulation versus in the real world for the trajectory error of the SDV? But there are other metrics we can compute to really understand at every single component of my autonomy system, am I able to reproduce a similar behavior? We can look at the original point cloud reconstruction metrics and image reconstruction metrics, but also how well do I have good localization in simulation versus in the real world? Or do I get the same perceptual feature maps between sim versus the real world? Or am I able to get very high fidelity vehicle modeling of the dynamics based on the control outputs? These all feed into making a holistic evaluation of the simulation system's realism, which then fall into the safety case. And so in conclusion, we have two core components of waabi's autonomy system development process, the waabi driver and the waabi world, and both come together and are used to help develop generalizable, efficient, and provably safe physical AI systems. And if we go to the next slide, I think that's the conclusion of the talk. Apologies for the last minute notice, but yeah, thanks for the time. Sorry, did someone say something, Jin-Kong?
Yeah, thank you, Siva and Jin-Kong, for this great talk and the kind of walkthrough over the waabi world and waabi driver. We might have time for one quick question before we move to the panel discussion.
Hey there, I just want to ask about the flux 40 method you described.
Yep.
How do you compute the target?
The recording has stopped.
Scene flow. It doesn't seem like the model would be incentivized to do that unless it has explicit targets.
Yeah, we don't have any supervision about that part. So basically, we just during the training, we predict the flow for each particle, and then we warp to the target view, and then we compare with the runs. And no supervisions on the object flow or no pre-trained vision models, and this will automatically run by training across many data.
Gotcha. Cool. Thank you.
Thank you. Thank you again, Siva and Jinka. Can we give another round of applause?
Thank you.
Max, can you share? Can you maybe share the slide? Yeah, sure. Shares. Okay, so this brings us to the final point of this workshop today. I know that we are all very tired, but I promise that this will be a very interesting panel discussion where we will confront opinions from different subfields of AV and AV simulation. So I have already introduced all of the keynote speakers before, so back joining us will be Drago, Johan, Carl, Marco, and Eugene. And the panel will be moderated by Sanja Fiedler, who is an associate professor at the University of Toronto, also co-founder of the Vector Institute and a VP of AI research at NVIDIA. We have prepared some questions, but we expect that an interesting discussion will emerge.